Okay, so let's look at some extensions of the big O notation. We'll look at omega and theta, big omega and big theta. Okay, so the reason we're looking at these is we want more precise boundaries. Currently, with just the big O notation, we can express the concept of an upper bound. So we can say that for some function f, that it is always at or below some other function g. But that's not very precise. We sometimes want to be much more specific. So for example, if we were talking about just regular numbers on the number line, this would kind of be equivalent to being able to express the concept of x being less than or equal to y, but not x being greater than or equal to y or x being equal to y. So we'd like more precise statements that allow us to express the concept of greater than, or the idea of having something that's a lower bound, and the idea of equal to, or something that's a very, very precise bound. So the first one we'll look at is big omega. So this kind of expresses the concept of a lower bound. We're going to start with a definition that's a lot like our definition for big O. So we'll have our two functions, f and g. They'll both be non-negative functions of some variable n, just like they were with big O. And again, usually we're expressing the idea of running times or memory, things that are strictly positive. Okay, so our definition of big omega. The function f is in big omega of g if there exists constants, c greater than 0 and n0 greater than 0. And again, these are kind of our scalar multiplier and our start point, such that for all values of n after n0, after our start point, the function f is greater than, so a little bit different than our big O notation, is greater than some constant c times g of n. So again, we're trying to establish that the g of n, this function, is a lower bound. It's always below the function f after a certain point. Okay, so before, just like before, we're going to look at kind of this geometrically. So if we've got two non-negative functions here, f and g, the idea here is that we've got some start point area, and that after that, we don't really care what happens before that, but after that, we say that our function g, even when multiplied by some value, is some positive value, is always below our function f. So again, it's a lower bound. It's always below f. Okay, so in order to prove this, to prove that some function is omega of another function, we've got another little lemma here we can use to our advantage. So f is, if f is in big O of g, if and only if g is in omega of f. So what this allows us to do is we can, in order to identify a big omega relationship, we can fall back to what we already know how to do with big O. So as an example, if we want to prove that n squared is in big omega of n log n, that is, n log n is a lower bound or always below n squared after some start point, what we can do is we can juggle these around and we can say that n log n is in big O of n squared. Okay. Okay, so let's try and prove this lemma, or at least prove one part of it. Again, we're trying to show that there's this relationship between the big O and the big omega, and it's an if and only relationship. So remember, this is kind of a two-way implication. Here, we're just going to focus on one direction. So we'll assume that the left-hand side is in fact true, that f is in the big O of g. And what we want to show is that as a result of that, we know that g is in the big omega of f. Okay? So kind of in English, what we're saying is that our function f is bounded above by g. And because we know that, we can say that g is bounded from below by f. Okay. So again, we're assuming that the left-hand side is true to prove the forward direction of the implication here. So we're just going to start with our definition of the big omega. The big O. And then we're going to do a little bit of algebraic manipulation. So we're going to pick a constant d that's equivalent to 1 over c. And so working off of our big O definition, we know that for the f to be in big O of g, this relationship holds true every place past our start point. We know that the function f is below some constant times the function g at all points. Okay, so let's take our constant d, which is equal to 1 over c. It's chosen to be related to our big O definition. And we know that c is a positive number, so we know 1 over a positive number is also a positive number. We can multiply both sides of that inequality by d, so d times f of n would be less than or equal to c times d times g of n. Okay. Okay, and then of course c times d, it's c times 1 over c, so that cancels out. So we've got d times f of n is less than or equal to g times g of n. Okay. Okay, and of course this inequality we can read backwards. We can say that g is greater than or equal to d times f of n. So what that's saying is that f of n is always below g of n. So essentially it's bounding below g of n. Okay, so with that we can kind of conclude that for some constants d and a start point n0, that our function g is bounded below, is in the big omega of f. Okay, so we've proven, again, just one direction of this if and only if. We could use a similar argument to go backwards and prove the other direction. So we won't do that here, but that's kind of the outline of the complete proof. Okay, so let's look at our third notion here, the big theta. So theta is kind of equivalent to equals, to two functions being essentially identical, except for the scalar, the multiplier difference between them. Okay, so just like before, we'll start with this idea of two different functions, f and g. They'll both be non-negative functions on n. Again, they represent either running times or memory, things that are strictly positive anyway. And our definition is that our function f is in the theta of g if there exists constants. In this case, we've got two constants, c1 and c2, and still a start point, n0. And still, we're only interested in things after the start point. So here, what we're doing is we're saying our function has to be bounded both above and below by our g function. So it's putting a very tight bounds on f. Okay, so graphically, the big theta looks something like this. So we've still got our two functions that are non-negative functions, just like before. It's in the same quadrant of our plane. Okay, and now our actual definition of theta is that our function f is bounded both above and below based on some sort of multiplier of g. So it's tightly bounded on both sides. Okay, so if we want to prove something about a particular function being in the big theta of another function, we again have kind of a lemma that gives us some guidance about how to do the proof. In this case, in order to do a proof, remember that the theta is about having a boundary that's really, really tight. It gives you some guidance on the lower bound and the upper bound. And essentially, in order to prove it, we have to prove both of those. So we have to prove that our function f has an upper bound and a lower bound. Okay, so as a more concrete example, if we want to prove that 3n squared plus 11n is in the theta of n squared, so basically there's some concrete multiple of n squared that bounds us above and below, we have to prove two different things, that 3n squared plus 11n is in the big O of n squared, and also that it's in the big omega of n squared. Okay, so unlike a couple of the previous examples, we are not going to review or outline a proof for why this particular lemma is true, but that's something that you should be able to prove based on the examples we've already gone through and the definitions of big O, big omega, and big theta. Okay, so finally, some conclusions. We've now got tools for a precise way to bound behaviors of functions when n gets large, and ignoring constant factors. So again, this gives us a really solid way to compare things in a relevant way that we want to compare them. We can replace ugly precise running times by much simpler expressions with the same asymptotic behavior. So earlier we saw examples where we kept track of every single detail, but oftentimes they're overshadowed by the larger order component. So for example, if there's an n squared plus 3n, the 3n term will be overshadowed by the quadratic term. So we'll essentially discard it. Okay, and in this class, you will see these three functions quite frequently. So get used to them, be prepared to be able to do convincing proofs comparable to what we've done today.